So in the last session, we fairly understood, right, what is machine learning, different types of machine learning, and what is a model, right? Then looked at some of the challenges as well, right? But more, we are still yet to explore on challenges and other parts, right? We have looked into, if you remember, very important concept is types of machine learning: supervised, unsupervised, semi-supervised, and reinforcement learning, right? All these four were covered, and some of these techniques we are going to touch also practically, right? Specifically the supervised ones, and maybe if there is a time is there, right, we will touch upon unsupervised ones as such, right? We have looked into various examples and all. Now, what are the types of learning, right? One aspect is supervised, unsupervised. That's an approach. Another is when I have a data with me, right? I usually do what? I'll split my data into two parts. That's training data, right? And there is a test data. Whatever is the data is given to us, just let me write here. There is training data, right? And there is test data. So what training data does is, using the training data, we train a model. And before we deploy it, we're using the test data, we test it, like how it is performing overall. Now, when we are training a particular model using the training data, it could be in the form of batch learning, where I'm going to use all the available data at a time during training. Whatever I've said, okay, this is the data I'll use, and I'm going to train my model at once. Then there comes a mini batch learning, which uses a subset of available data. I'm not going to use the complete data. Rather, I'm going to use a subset of data at a time for training as such. There's an incremental one where the data keeps on adding and model keeps on learning as such. Look at these diagrams also. You have some data, right? Using that data, you train an ML algorithm, you evaluate a solution. And if you are not satisfied with that, you're kind of going to come back and retrain it or do some tweaks to it. Otherwise, you launch it, right? And then there's new data you have to run on the fly. You can learn on the fly from the new data, right? On the right side, what you see is when I have lots of data, right? This is about mini batch learning. So I am going to divide my data into pieces. So I'm not going to feed all the data. I'm going to train an algorithm as such, right? Obviously, for which the problem has to be studied first. I'm going to train an ML algorithm, evaluate a solution, analyze errors if there are any, like I'm not satisfied with the performance, I'll go back, redo the things, right? And then if once I'm satisfied with the evaluation, I'm going to launch the model for the unseen data. Now look at another type of categorization where you see instance-based learning and model-based learning. Now, whenever there is a new data points that are coming in, right, what you can do is you can look at the new data, I mean, the nearby data points. Let's look at the left diagram. What you're able to see is the yellow ones, right? This is my new instance as such. Sorry. Yeah. This is my new instance. And when I'm going to compare the new data points to the known data points and then categorize them as such. If you look at these new instances that have come in, right? The two green ones in the triangles and one square in the yellow, all these are the new instances. If you look at the triangles, right, they are more closer to the triangles which are there in the existing data. So I'm categorizing them as triangles, right? And if you look at the square, it is more closer to the square, right? So I'm categorizing it as a square as such. That's an instance-based learning, basis which I'm categorizing my new instances. On the right side, if you see, this is a model-based learning, right? Sorry, this one, where I have drawn a boundary like this, right? I've drawn a boundary like this, where it says, okay, these are the triangles, and below this boundary, there are squares, right? So whenever new instance comes in, I have to see on which side of the boundary it falls, basis which I will categorize. And this is what is a model-based learning. So when I talk about a model, right, we've talked about a regression problem. I talked about a straight line or a curve. So based on the position of the straight line in the curve, I am going to categorize the new points if they fall above the curve or below the curve as such. Okay. Looking into the challenges, we will talk about it one by one. These are very important, starting with training data, model selection, and testing and validation. Okay, just give me a moment. I think new people have joined just right. They can just look into. I mean, if they have any questions from the previous session and all, they can simply type it in the chat box. I'll look into all those questions. Hello, are we well connected? Hello. Today the response is slow. I don't know why. Okay, what are the challenges now that may exist when you say, okay, I'm going to apply machine learning, right? What are the challenges that may exist as such? When I talk about a training data, right? It may be insufficient, right? As such, it is a non-representative of what we want to model as such. So the training data does not contain the required information as such. It may be of poor quality because when you deal with the real life data, right, it may suffer from quality issues. So if I'm going to feed a poor quality data to my model, the performance would not be that good. So I need to deal with that quality issues first. There are irrelevant attributes, right? These are the challenges that do exist with respect to the training data. When it comes to model selection, right? My idea is to generalize the things, right? I don't want a model to be uh, kind of, you can say, um, whatever the data I have given to it, it aligns very well to that particular training data. But when I'm giving some other data, right, which it has not seen, so it is not performing well on that, that we don't want, right? And that term is typically known as overfitting. With graphs and all, I'll explain overfitting in detail. There is another term used as underfitting. Underfitting is something when the model itself is not very well aligned with the training data, right? So that is termed as an underfitting. And then comes testing and validation using hyperparameters and all. Now, what are hyperparameters? We will learn, right? What do we mean by hyperparameters? Insufficient training data. Look at this example, right? When we do not have enough training data and we want the model to perform as such. So you look at this, we on the one side, we have a kind of training data and the accuracy on the other side as such. And what are these lines that you are seeing is there are different machine learning models as such. The memory based, Vino, Perceptron, Naive based, and so on, right? What is happening? If you see the curve, right? Whenever there is a smaller data, if this point is here, right? This is a smaller data, right? The accuracy is also small. The moment you increase the data, accuracy is also increasing, right? And the moment you keep on increasing it, the accuracy keeps on increasing as such, right? When you have got 1,000 millions of words and you see the accuracy is also touched 95% almost, right? For all the models. So what is the accuracy that we are targeting, right? Basis that we have to set, okay, this much data I should have with me in order to solve the problem effectively, right? So this is one trade-off, right? If you do not have a sufficient data, you cannot expect a reasonable accuracy of the performance metrics from a machine learning model. Another example is the training data be representative of the new cases we want to generalize, right? So when we do a sort of sampling, right? Do you know what is sampling? Will you say something yes or no by unmuting yourself? Or should I keep on speaking? Is this way the contact session should happen? I think earlier also I've taken at least few students will definitely respond. I'm not sure what has happened. Is it too difficult? If you don't give me a response, how the class will be effective? Hello? Hello? Shweta, are you there? Shweta, are you there? Shreya Sarkar? Hello? Maybe at times I have to see what is going on, right? Hello? May I have some response, please, if you are able to understand this or not. Are you able to hear me first? Can somebody please give me some response? Hello? Why you are so lazy in the morning itself? Have come on a weekend to attend a class, right? So then it should be interactive one. Are you able to follow? See, if you don't read the previous thing, this is something new that most of you told me that we do not know anything about this. We haven't worked in this area. So obviously you need to put up some effort for this. And if this is the level of motivation that you've got, like, okay, if the faculty is even asking, okay, if you are able to understand or not, you are not bothered to respond. See, this is an online class. I cannot read your faces here. See, if this is the level of motivation, then you will have to do it yourself, most of the things. Kindly take notes, attend every class so that you are in line with what is being covered and what next I am going to cover. You should have a look at it, your notes at least, what was covered in the last session. And we have almost finalized the EC1 components also. So throughout this course as such, you will have to submit one or the other aspect. This way we cannot proceed the way you are behaving as such. There's a lot of lab oriented stuff we are going to have soon. If you are here, kindly ask questions. At least if I am asking, okay, give me some response if you have understood or not. This way I cannot proceed further. And there are some 15, 18 people have joined. Why you've joined when you cannot respond? It's a two-way thing, right? It's not a one-way thing. And even you also cut the faculty's flow also. So when we say non-representative training data, what does it mean? Because everything the model is going to learn from the training data. If training data is not a true representative of the real world cases, right, on which later the model will make predictions on, right, then the model will not be performing very good as such. There is a small sample size that can introduce even sampling noise. So typically what happens when only a few data points are available, whatever is the observed relationship may not represent a true pattern in the population, right? When I say sampling, right, you must have seen opinion polls. Are they going to each and every person and ask, okay, what to whom you prefer, which party you prefer, and so on? No, they are going to subset of people in one particular area. And how good they choose a subset, that is the representative of the true population, right? If they only go to, let's say, the shopkeepers, the business person, they'll have a different perspective. Somebody who's a salaried, they'll have a different perspective. Somebody working in a private sector, they will have a different perspective, right? Somebody being a driver, they will have a different perspective. But if my sample only includes one of these and they don't know the opinion of, let's say, people who are driving vehicles, right, maybe autos or Uber cars and so on, will that opinion poll that is an outcome, will that represent the kind of true election results? May I have some response now? If I only go to certain people, right, certain subset of people as such, and then start making opinions, okay, this party will win. Now, I don't have the data. Maybe I've only gone to urban people. There are a lot of people who stay in villages. They might have different sets of challenges. So their preferences may be different. So if my sample is going to be not containing appropriate data points from each sector, my outcome is not going to be good. I hope this point makes sense. Can I get some response, please? Now, still, see, this is the way I cannot proceed, right? You can unmute yourself. This is a facility given to you. Unmute and speak. Say yes, no, or you want more examples, do let me know. Session is for you. The program is for you. These 2 hours are being dedicated for applied machine learning. So make the most out of it. And this is very much relevant area nowadays, being practiced in every organization. And once you understand the fundamentals, you can pick up the problem from your domain and apply it also. But the only problem is you have to devote time on it. And once you start devoting time, of course, you will feel connected with this particular course as well. Okay, now what this chart is saying, there is a life satisfaction, there is a GDP per capita, right? So basically, kind of more wealth the country has, is it like that? The more the people are satisfied there as such, right? That is the case. So if you look at the blue dots, those are the available data. But if you look at the red dots, right? The red squares as such, that is the missing data. Those are the countries like Brazil, Mexico, Chile, Czech Republic, Norway, Switzerland, Luxembourg, and all. Right? When you try to model that particular situation, like this is a straight line that can pass, right? As such, if that data, right, whatever the red ones are, the red squares that represent the missing countries or the missing data points, right? So solid line represents the trend learned from the available data, right? There's one line going here. Right, this one. This line. And it also suggests how the trend could change if the missing data were included. So if I only pick up the blue dots and try to model, I'll have a different model, right? When I try to also include the missing data, which was not there. So for some countries, the data was not available. Now, if I get to know, okay, the data of Brazil, Mexico, Norway, Switzerland, and Luxembourg, and so on, right? The model learned will be different. So if I only use the blue dots, right, then of course, whatever the countries that are missed out, it may not model well for those countries as such. So let's say if only wealthy countries with high happiness scores are included, the model may conclude that increasing GDP always increase happiness. But the moment the missing countries are added, the red ones, the trend becomes more balanced and realistic as such, right? The trend becomes more balanced and realistic. So the major takeaway is that machine learning models are only as good as the data that we are using to train them. So training data must be diverse, unbiased, and representative of the real world cases. missing or biased samples can lead to incorrect generalization and poor predictions. That's what typically this chart says. So if only the blue ones are there, you see this portion as such, right? But the moment you add this, the model gets changed, right? That's what it is. Another issue we talked about is data quality, right? Of course, many of the real life data sets, they suffer from the quality issues. Quality in terms of maybe do you have missing values in the data set, right? You typically fill surveys and deliberately you left something right as such, okay, this is with what will not fill. Specifically your feedback survey, if I talk about even, right? You'll give some numbers and all, but you will never give a scope of improvement for that. Even now I am asking something, you are not ready to speak, but you will simply have a way of categorizing the faculty members, okay, this is what it is, right? So there's some missing value as such. And even in other surveys also, which organizations collect to do certain analysis, if something is left optional, of course, that will go missing as such. So there are missing values, right? Because people don't want to specify their age, right? Or there could be any other attributes which people don't want to reveal as such. So how to deal with them, right? So either is we have to fill in those missing values. I can ignore those instances where there are missing values, right, as such. As well as there can be some instances which can be erroneous, meaning that there is a noise or there are outliers within that, right? This could be human or machine generated. I am noting down some temperature, but my thermometer is faulty. What will happen? It will give some inflated readings, right? It will give some biased readings as such. Some noise is getting introduced because my machine is faulty. We need to identify all such things, discard or fix manually as we feel appropriate, right? So these are some of the data quality issues. More we will touch upon soon. Then comes feature engineering, right? We have talked about it. We said that, okay, there is a training data, you feed it to the model and then start training it. But data size may be huge. It might have a lot of features as such, right? Maybe if I talk about customer, there could be customer ID, name, right? Uh, age, date of birth, right? Place, and there could be so many features, right? Do all the features are equally important when I'm going to do certain kind of analysis? Or I can limit the set of features uh, which I want for a certain kind of analysis, right? That's the call we have to take once we do a feature selection. I'm going to pick up only useful features. I'm not going to pick up all the features from the data. Now I have to see which are the useful features. So I'll do some feature selection. For example, let's say I want to predict the CGPA of the student. Do you think the name of the student play an important role to predict how much a CGPA or how much is the score that student is going to score going to get in a particular course or in a particular program? Does name play any important role? May I have some response? Does name play any important role? When I want to predict, let's say, CGPA, does it make sense? Okay, if the student has this particular name, yes, the CGPA will be high. If the student has this particular name, the CGPA, does it make sense? No, no, it does not make sense. So what makes sense is certain features. Okay, how many hours of study student is given, in which particular domain he is working, right? Has he attended all the classes? Has he attended all the evaluation components? These are the more relevant features that I need, right, for predicting a student score as such. But I don't think the name is going to play an important role. Then comes the feature extraction. I'm going to combine the existing features to produce a more useful one. One example I've given you, okay, mass per unit volume is the density, right? So if I have two things, mass and volume as such, as two features, but I can only come up with a new feature that is density. That's a feature extraction I am doing. I can create new features by gathering new data, right? So feature engineering is an important step that has to be done before you start feeding the training data to the model. You have to decide which features should go to the training data. I talked about overfitting right earlier. Model selection. Should I go for overfitting or should I go for underfitting? I have to avoid both the things. Now, what is overfitting? When I'm going to train the train the model using a training set, right? The model will learn perfectly some weights from the training data. Like these are the rules I have to learn, or this is the mathematical equation I have to learn. Now it aligns very well with the training data. But in the test data, there were certain cases on which the model was not trained enough, right? So it is not a generalized. When we tested its performance on the test data, it didn't perform well. So that is termed as overfitting, right? So if you look at this particular diagram, right, what you see here is these are the points. These are the points. And you see these are the points here. So what the model is trying to do here is it is trying to fit all the points almost. You see, very well closely passing to the points. And when I have this kind of a model which perfectly aligns with the training data and come up with a complex curve like this, which is a higher order polynomial curve, so this will result in a overfitting. The moment you give it a test data, it will not perform that well. When you look at this data, this particular model, it's more generalized one, right? As such, and it's more generalized. And when I give it unseen data, it will give me some better predictions than the overfit model. But there is another extreme of underfitting as well. Underfitting means that your model is not aligning itself with the training data. Model is too simple to learn the underlying structure of the data. So maybe I've just picked up, let's say, linear regression, a kind of a straight line where I need a polynomial curve, right? That will be too simple, right? So what we need to do in such cases is I need to select a more powerful model with more parameters, right? Maybe I need to feed better features to the learning algorithm, right? And there's another method that we use is the regularization part, right? This regularization is actually used to reduce the overfitting part, right? But we should not increase the regularization to a level that model underfits. Right? So we have to be careful about both the extremes. We want a generalized model. We do not want a model to be overfit. We do not want a model to be underfit. Look at these examples also. So these are the charts, right? The first one, it says underfitting because I've come up with a straight line, and straight line, you see there are some points on the right side with a cross as well as with a circle. Here also you find cross in circle, right? But when you look at it, I came up with this curve. Still, there is some error that these two cross, but this is more of a generalized one. Imagine now, I'm trying to overfit. I am going to each and every point and see how complex curve is coming out to be. See, this decision boundary is too much complex. So this is overfitting. We should avoid this, right? Because when I'll see the unseen data, this may actually perform poorly in comparison to this, right? So we want a generalized model. We don't want underfitting. We don't want overfitting, but we want an appropriate fitting as such. Does that make sense? Does that make sense? What is overfitting, what is underfitting, and what is appropriate? Only 2 students responding. Still, there are 17 more students. Look at this now. You have an output variable, you have a predictor variable on one side, right? So this is a plot that is coming out. So actually, this more suitable model is a kind of a curve like this, right? This is automatically drawn, right? More suitable model is a kind of a curve like this. But when you look at this, right, this is an appropriate model. But when you look at this, which is trying to pass exactly through each and every point, this is an overfit model. So straight line would be an underfit. And if you come up with a too complex curve passing through each and every point, it will be an overfit. And when you give a generalized curve, some points lie on that curve, some points above and below, but it is fitting in the shape as such. That is an appropriate thing, right? So that's an optimal thing that we want to achieve when we do machine learning training as such. Next comes is the performance of ML algorithm. Be attentive, keep taking notes, right? This will keep you alive in the session. Testing and validation. Testing, we already know what testing is, right? What is validation? That is what we are going to learn. So performance of ML algorithm, the first point says it's statistical or predictive in nature, meaning that the machine learning models are not judged only by how well they memorize the training data, but how accurately they can predict the outcomes on the new unseen data. Look at our email classification example, spam or not spam. So it does not mean that, okay, it is aligning very well with the training data, but when it comes to unseen data, the new emails which it has not seen, it is not performing that good. So that is not a good performance overall, right? So how well it can predict the future unseen data, that is what the performance of an ML algorithm is. So the first point says that any good machine learning algorithm should work well on the test data first, because test data we do not give it, right? Only we give it training data. So once using the training data, it has learned certain parameters, and then it is apply all those things on the test data, and then we try to compare. The output is there with us, what the model predicts and what is the difference. So test data is kind of completely unseen data for the model. And the real objective here is not the memorization, but the generalization, the ability to perform well on the future unknown cases. Next is, we have a common assumption, right? That training data is representative of the test data. But that depends on how I have chosen that, right? If I randomly select subset of the training data, right? Um, which may not be modeling all kind of cases as such. So let's say I have some 100 cases. It is a classification data. So maybe let's say 50 belongs to class A, 30 belongs to class B, and then 20 belongs to class C. I picked up some 60 cases to train the data, and I missed the class C there. I missed taking the class C representatives there in the data. So I have randomly chosen it. So what happened? The training data is not a true representative of test data in that case, because test cases now will have a representatives of class C, while in training I have not fed that. So that's another problem, challenge you can say. So what you typically do is there's something called as a validation set, right? A randomly selected subset of the training set, training data is a validation data. It's around 20 to 30% of the data we reserved for a particular purpose. So there's one training set and there is one validation set. Training set is used to train the model. Validation set is used to evaluate the model during development. So from the training set, the model will learn the parameters, right? After training, the model is tested on the validation set first. If model performs well on the validation data, we expect it to perform well on the test data also, right? Let's take an example. Let's say I have 1,000 student records for predicting whether a student will pass or fail. 100 records may be used for training, not only 100, 800 I can say, right? Let's say 800 records will be used for training and 200 records I may use it for validation. And model will learn certain rules or equations from 800 records and then evaluate it on the remaining 200 unseen records. And if the validation accuracy is high, it suggests that the model has learned meaningful patterns rather than simply memorizing the training data. So the key takeaway here is model must be evaluated on the unseen data. Validation will help you to kind of estimate how well the model will generalize to the real world test cases. And of course, proper data fitting is splitting is essential to avoid kind of overfitting and build reliable predictive models as such, right? There's another technique that we're going to talk about is cross validation. Any questions on validation? Any questions? Are we good with so far what we have covered? Okay. Anybody else? Okay. Now let me move to the K-fold cross validation. It's a common technique used to evaluate machine learning models more reliably. So basically what we try to do here is we are trying to reduce the bias of the validation set, which may occur when we select only one validation set. So what may happen is sometimes model performance may look very good or very poor, both extremes I am talking about, simply because a particular data is chosen for validation. When I do cross validation, it helps me to overcome this issue. I'm not going to test my model one single time. Now I'm going to test my model multiple times on different subsets of data. Now, let's say k is equal to 10, which is called as a 10-fold cross validation. So what will happen in a 10-fold cross validation? I'm going to divide my entire data set into 10 equal parts, which are nothing but called as the folds of that particular data. So one fold is selected, right, as a validation set. The remaining 9 folds are used for training. So let's say I have 1,000 records, right? So I will divide it into 100 records each, right? And I have 10 sets of 100 records. Out of this, what I'm going to do, I'm going to use 9 sets for the training, 1 set for the validation. So in this way, I'm going to kind of cover all such cases, right? The model is trained and evaluated. And the process is repeated 10 times in case of a 10 cross validation, right? K cross validation when K is 10. The performance of all the 10 runs, I'm going to take an average of that. That is my model performance now. So first time I picked, let's say, first 900 records for training and last 100 records for validation. Next time I have picked up, let's say, first 800 records and last 100 records. Total 900 for training and maybe 800 to 900 records. It's the sample size starting with 801 to 900. I picked up for validation. Third time, maybe 701 to 800 I'll pick up for validation. Rest 900 records I'll use. So in this way, I will train 10 models and see the performance of 10 models, and then I'm going to take the average of each. Right? I'm going to take the average of each. So I'll have a better estimation of the model performance. I'll reduce the dependence on one random training test split as such. I'll have efficient use of limited data. And of course, this will also avoid overfitting more reliably. Next comes this choice of hyperparameters. So we will look into this in detail at some other point of time also, but let us learn what is hyperparameters as such. Little bit as of now. Many machine learning models often use a lot of model parameters. Those are typically termed as hyperparameters. And the performance depends on those hyperparameters also, choice of hyperparameters. So each parameter can assume a number of values. It could be real numbers or categories, right? So when I have certain hyperparameters, right, there are a lot of combinations of such hyperparameters possible. Let us say I want to come up with grouping of the data, right? Grouping means cluster I want to form and based on the similarity to each other. So given the data set, whether I should come up with two groups or two clusters or three groups or three clusters or five groups or five clusters, I don't know, right? So that's an hyperparameter. How many number of groups or clusters I should come up with? If I come up with two only, I might have a different performance, but when I go for a five, I might have a different performance as such. Right? So that is one kind of a hyperparameter, right? And if there are more hyperparameters, there are certain combinations also, right? More I'll explain once we cover an algorithm on it, right? And what is a hyperparameter and how does it play an important role as such by experimentation, right? And we need to sort of optimize these hyperparameters. For that, it's of course expensive to perform that because you need to do the model tweaks time and again to get the accurate hyperparameters. So best model correspond to best cross validation performance over set of hyperparameter combinations. So I've set certain hyperparameters, right? Like I said, number of clusters, the number of groups. That if I want to come up with two groups, I'll have different hyperparameters. If I want to come up with three groups, I will have different hyperparameters. I mean, three is the hyper. So I'll have different performance also altogether, right? So sort of, I'm trying to come up at what particular value of that hyperparameter the model is performing best with respect to the given data. So I'm interested in choosing that best possible combination of hyperparameters. So that is all from the session one on this, right? So we've spent good amount of time. So let me move little faster, and now the things are set up. We can move a bit faster now. So chapter 2 is also very similar to the session 2 is also very similar to the session 1. Many of these things we have already touched upon in our last 2.5 sessions that we have spent, right? And now some of these things will be repeated, and I will just quickly go through those things. But wherever we need to spend time mathematically, I'll spend that also. Let's look at some key elements of a machine learning project. The very first thing is, how do you frame a machine learning problem, right? What are the what do you need? Most of these things we have already looked into, right? But I am not going to apply machine learning on every kind of a problem that I face, right? I may solve it using some deterministic algorithm as well. And there's no need to apply machine learning on that, right? So I need to frame my problem carefully. Otherwise, most of these projects fail because it has not been framed carefully. Then what sort of data types and representations I should look for? What is the pre-processing, right? I said data suffer from a lot of quality issues, right? It could be missing values, it could be outliers, noise in the data. So we need to remove all such things before I feed my data for training a model. Visualization and analysis important. What kind of different plots are available to uh, analyze the outcome, right? Understand the relationship between different features and so on. Feature engineering, we have touched upon, right? What exactly it is. And then finally, model building and testing, right? Let's start with a bigger picture. Let's say you want to come up with a model of housing prices using the census data as such. The very first thing is, okay, you need to figure it out that, okay, what kind of problem it is, right? Okay, you want to apply machine learning, fine, but figure it out what kind of problem it is. Let's say if I talk about two things, which we have covered in our chapter 1 or session 1 as such, is regression and classification. Regression is all about predicting a continuous variable, while classification is all about predicting discrete variable. We talked about email classification problem, right? We talked about predicting house prices earlier. So one of them is regression, while email classification is a classification problem. What kind of problem I am looking forward? Is it a regression or a classification or something else I'm going to do, right? That's the first thing. Once I'm done with that, do I have the relevant data? What sort of attribute should I look for, right? So what is the data that I need? What are the attributes that I should look for? All those things should be taken into consideration, because without data, you cannot train a model as such. So then model is going to predict something. In this case, the example which is written here is median housing price in any district given all other metrics as such. So that is what it is going to do. So then third thing is, how do I look at the goodness of a model? I have now data. I said that, okay, my problem falls under regression or classification, the way I'm looking forward to. This is the problem exactly. I've defined what I want to predict. I have sufficient data. Now, model will do training and start making predictions. How do I evaluate whether it is good or bad? Of course, I need to check the model output with the actual price, right? For certain unseen district data as such, and then I can say whether my model is good for deployment or not, right? This is all we have covered in the last 2.5 sessions also, and same diagram as such, that you need to understand the business objective first. I want to solve a problem. Is it going to, when I talk about a corporate, right? They'll first understand what is the use case, what is the expected benefit out of it, right? So you need to understand the business objective and the context to which you want to apply ML as such. So for that, you will need to do certain kind of analysis. Then you have to prepare a proposal. Okay, this is what is going to happen, and so algorithm. This is the goodness measure that I'm going to use, and this is the effort in life cycle management of the model as such. That's fine, right? What is the baseline method and its performance? Because I want to benchmark also. Right? So these are some basic fundamentals that I should look at when I'm going to apply machine learning. Choice of model, right? Whether it comes to choice of model, that can be in multiple ways. One is, of course, whether I want to use supervised techniques, unsupervised techniques, or whether I want to go with the reinforcement or semi-supervised, right? So choice between different techniques. First is, let's talk about two broader, supervised or unsupervised. Now, maybe if I'm going for supervised, should I go for prediction or classification? Should I go for online versus batch training? Should I go for instance-based model learning or model-based learning? All these are the questions that we need to answer when we are choosing a model. So then we have to look at the data set, analyze the data set. When we look at the data set, each instance comes with expected output, which is the district's median housing price, right? So there is already some historical data available with you, so it becomes a kind of a supervised problem. The goal is to predict a real valued price, right? Because price is real valued, continuous in nature. So it becomes a regression, right? So output is based on the input data, not rapidly changing data, right? So data set small enough to fit in the memory, so I can go with a batch. If it is large data, right, which cannot be fit into the memory, so it will require a lot of time for training, so I can divide them into batches and then train, right? So basis this, I have to say that, okay, what kind of problem it is, right? Then I said, you will have to choose certain performance metrics. When I'm doing a regression model, what I'm trying to predict is how close it is to the actual prediction, right? Regression model has given me some prediction value, let's say 25 lakhs, right, for our problem. The actual is, let's say, 25.5, right? So there is some difference between the actual and the prediction, right? So what this RMSE finds out says root mean square error, the difference between the predicted value and the actual value for all the observations, right? And then we are squaring it and dividing it by m as such. This gives me RMSE. So the difference between actual and predicted, right? Our objective should be to minimize this overall, right? Because I want to be as close to the actual prediction. So I know the actual prediction. Now I'm testing my model, right? I will give certain input features to the model. Model will give me prediction. I'll compare it with the output that I have already available with me and see the difference. Right? So there are multiple metrics that I can use for typically a regression model. One is root mean square error. Another is mean absolute error. Mean absolute error is simply the difference of the prediction and the actual. Sum it across, divide by for m number of observation. That is what it is, right? So this is basically the generalized form of both. So if you put k is equal to 1, right, this is mean absolute error. If you put k is equal to 2, this will become RMSE, right? I hope it is making sense that what is this root mean square error and mean absolute error, and why do we want to minimize them? Is it making sense or not? Hello? See, don't be quiet. I'm looking forward to a response. Shreya, are you there? Okay, let me move forward. Now, check the assumptions. There are always certain assumptions that we make, right? Verify whether the downstream module actually uses the real valued prices rather than processing them into, say, categories, right? So whether the model which I was trying to get right, if let's say I'm not uh, very well satisfied with the performance and all given the data set, right? So I need to step back and see whatever the assumptions I made, was it correct or not? Is it actually predicting the real values or the categories? Basically, earlier I assumed that okay, it is a regression problem, but when I didn't get the right results, I may need to check it. Was it really a regression problem? So if yes, then I may have to try some more advanced techniques for fitting a model for regression. Or I need to check if it is a better a classification problem or not, right? So before we deploy this, right, when we are actually training or designing a model, these things should be checked out, right? Otherwise, it may lead to certain potential hazards if you are actually deployed it and then trying to use it, right? Next comes is the type of data that we have. We all know what a data is. We have studied a course on database systems and applications already. So we know what a structured data is, which is stored in the form of tables as such, right? And we know there are attributes within the table, there are records, each row is a record, each column is an attribute, and so on, right? So basically what attributes describes is an attribute or characteristics of an object. Eye color of a person, temperature, right? All these are the attributes. Collection of attribute describes an object. So if you look at this particular table, so refund is one attribute, marital status is another, taxable income is another attribute, and this is another attribute, right? So all four are sort of attributes. So now what might happen is we have to see how many different attributes are there, right? To which, what is the kind of data that they store? If you look at refund attributes, right? It is storing yes or no values. When you look at marital status, single, married, divorced, it is also storing these kinds of values. When you look at taxable income, it is storing some numerical value, right? 100K, 125K, 70K, and so on. So I'm more interested in these. What is exactly the type of the data that each attribute is going to store, right? What is important is when you look at an attribute, right, the values could be stored differently. When typically the data comes from multiple sources, this may happen. That in, let's say, one data has stored the height of a person in centimeters, while other data has stored it in meters, and so on. So the attribute is same height. However, the kind of values they can take are different, right? So we need to work with all these kinds of things, right, as such. So basically, what is the takeaway from the chart is it's just talking about a data in the form of a table that you have one row equivalent to one real life object, collection of objects form a data set as such, right? And when you look at an attribute, right, it's a kind of a feature that is what we are looking at in the set of values it can take in one particular column. It indicates that, right? What is important now is discrete and continuous. I've already talked about is discrete is which something you can count as only a finite or countably infinite set of values, right? That is a discrete attribute. Email classification, spam email, non-spam email, discrete valued, right? I want to predict the house price. House price can take any value. So there are infinite values possible. So they have correspondence to real numbers as such. So that's a continuous attribute. When you look at another example, let's say when you look at zip codes of a particular country, right? These are discrete valued. Reason being that each zip code is discrete and these are finite zip codes available as such, right? So that is why that is a discrete. When it comes to, let's say, temperature, temperature can be anything 20.1, 20.2, 20. So infinite values it can take. So it becomes a continuous attribute, right? So continuous attributes are typically represented using floating point. Right? Now there could be some binary attributes. Like if I talk about gender, gender is a male or female, right? There are special case of discrete attributes as such. When I go back to this data, if I look at refund or marital status, what are these? Are they discrete valued or continuous? A quick answer would help me if you have understood or not. Are they discrete valued or continuous? Discrete. When you look at taxable income, continuous, correct? When you look at cheat attribute, is it discrete or continuous? Discrete again, good. So there are discrete attributes, there are continuous attributes, right? Another variation, right? There are four different types of attributes you can say. One is nominal, the another is ordinal, third is interval, four in ratio. Very, very important, and we will see how to deal with each these attributes with a different set of techniques when we typically do some sort of processing with them. When you look at nominal attributes, right, you can typically perform one kind of operator with them. I mean, that is either you can compare this values equal to or not equal to, right? That's it. And typically these are categorical attributes with further restriction that only two sets of operators you can apply. Either it is equal to or not equal to. For example, let's say color. Color could be red, blue, green, and so on, right? Any color it could be. But it is discrete valued, right? And it is nominal. You cannot say red is less than blue and blue is greater than green. That kind of things you cannot say. You cannot also say red plus green. It does not make sense, right? And green plus blue does not make sense as such. If you are trying to do some mathematical operation with, okay, red is less than blue, blue is less than green, that kind of things do not work with these nominal attributes. The good examples are ID numbers, eye color, zip codes. These are all nominal attributes. So when I say ID numbers, you have your bits IDs. Does it make sense to add two bits IDs? Does it make sense to add two bits IDs? No, right? Another category that comes is ordinal attribute. Ordinal are again categorical in nature, but they have some order. For example, your grades, right? You got grades A minus B, B minus C, C minus D, and E, right? These are the grades that you typically get. But they have an order. A is the highest grade, then A minus, then B minus, and then C minus, and D. Right? They have certain order. So when you see the values uh, have certain order, then those are termed as ordinal attributes, right? If whenever you go and buy a certain apparel for yourself, right? So it says it has sizes small, medium, large, and so on. What is this? This is an ordinal attribute as such, right? So examples given are taste of potato chips on a scale from 1 to 10, right? Grades, height, right? So these are all ordinal. So you can apply less than and greater than along with equal to, not equal to. You can apply these two operator, less than, greater than, and so on. But still you cannot apply sub addition and subtraction or multiplication or division with them. It does it make sense? If you add two grades A and A minus, it does not make sense, right? And you cannot add two heights and all, right? Tall plus tall, it does not make sense. Tall is less than medium, tall is greater than medium, we know. Medium is greater than short, we know, right? If I look at sizes, small is less than medium, medium is less than large, we know. But what is the difference between them also, we don't know. We cannot say what is the difference between small and medium and large. That also we don't know. So, but we know there is some order. That's all. Then comes interval, right? Interval are the numeric attributes. First thing is these two are kind of, I can say, categorical. These two are numeric. Interval is a numeric value, right? Like your calendar date, temperature in Celsius or Fahrenheit, right? This is interval basically. So you will, along with equal to, not equal to, less than, greater than, you will be able to do addition and subtraction. But still you are not allowed to do multiplication or division with them, right? Can you multiply a date by 2? Does it make sense? You can say that today is this date, I can add 7 to it, and what will be the day after 7 days, right? That makes sense, but you cannot multiply it with 2, right? So you cannot divide a date by 2 or 3. That does not make much sense. And when you look at temperature in Celsius, which do not have an absolute zero basically. When I say absolute zero, if you have a temperature of 0 degrees centigrade, does it means nothing? When you have 0 degree, is it an absolute zero? This is not an absolute zero, right? I cannot say even that, okay, can I say this as, let's say, if some temperature is 5 degree and other is 10 degree, so 10 degree is twice as hot as 5 degree. Can I say this? 10 degree is twice as hot as 5 degree. Can I say this or not? We can say that. The answer is no, because we do not have an absolute zero. Does 0 degree centigrade means no temperature? I am talking about temperature in centigrade or Fahrenheit scale. I am not talking about temperature in Kelvin scale. That has a different meaning. This is very important concept to understand. What is the difference between interval and ratio? So when you have a temperature like 0 degree, right, it is almost kind of a freezing point. And when you have a temperature of 5 degrees, it's still cooler, 10 degrees more cooler. But I cannot say it is twice as hot as 5 degrees here. Or I cannot say 5 degrees centigrade is twice as cold as 10 degrees. It does not make sense to make a multiplication factor between temperatures when they are given in Celsius, right, or Fahrenheit. So those are interval scaled attributes where you cannot do subtraction, sorry, multiplication and division. When it comes to ratio scaled, right, those are the attributes where you can apply all kind of operators, right, whether it's equal to, not equal to, less than, greater than, addition, subtraction, as well as multiplication, division. The reason is, see, let's take about length, right? Now length could be 2 meter, length could be 4 meter. So I can say now 4 meter is double as 2 meter, right? Similarly for height, I can say 4 meter height is double the height as 2 meter, right? That makes sense because when I say length 0, it is absolute 0. It means nothing, right? Height 0, it means nothing. But when that I say temperature 0 degrees centigrade, does it mean nothing? There is some temperature. You will be able to feel that, right? That this is colder. Am I making sense or not? Are you able to follow? Okay. Study the what is the difference when you say 0 Kelvin, right, and 0 degree. You study what is the difference between that. Then it will be more clear. You can Google it out. That's good question, right? 0 Kelvin and 0 degree centigrade. It is related to something that the kinetic energy and all, right? If you look at that physical aspect, then it will be very, very clear. Even if you are using internet right now, put the difference 0 Kelvin versus 0 degree, because 0 Kelvin is absolute 0. 0 degree Celsius is not absolute 0. That is the difference. What gives you temperature sensation, right? That is what you will get. There's some kinetic energy things that are going, right? And at 0 Kelvin, what happens to that? At 0 degrees centigrade, what happens to that? You can have a look at that, and then it will make much more sense. Still, if you feel doubts, right, always come back to me with your study. Okay, this is what you studied, and then I will explain. Right? Length, I can always say 2 meter is half of, right, 4 meter. So I can apply this multiplication and division and it makes sense to it, right? Because length 0 means nothing. So it has an absolute 0. So I'm able to apply. But I cannot apply multiplication and division to interval scaled attributes. Another important thing is the characteristics of the data. One is the dimensionality. Dimensionality corresponds to the number of attributes that I am picking up. I might have 250 attributes, right? Should I pick all for the training? Should I pick all for the training or not? Let's say CEO wants to have a meeting. CEO of a company has so many employees. Let's say there are 50,000 to 1 lakh people working in the company. is it required that at a higher level meeting everybody should be invited? So what typically happens is the representatives of different business units, they go and meet the CEO, right? This is what is our business unit doing, this is what is our business unit doing, and so on, right? That is now what that head is representing, head of a business unit, it represents the complete business unit. Maybe there are 10,000 employees in that particular business unit, so he's a representative of that. When we have so many attributes, I can always reduce the dimensionality. We talked about one of the techniques in our last session, principal component analysis, right? So in that case, what will happen is when I apply PCA, PCA is a representative of so many attributes, and we have to carefully see how many attributes I can apply PCA and come up with a single representation of those attributes rather than picking up each and every attribute as such, right? So that is dimensionality reduction. Then comes sparsity. My data may be sparse, right? Look at the classification problem. Let's say data has, okay, this person has, let's say, a particular disease X, and this person do not have that particular disease X, right? So maybe people who have disease, they are very less in number, while the people who do not have disease, they are very large. So maybe I have, let's say, 1,000 records, 900 do not have disease and 100 do have. So that's a kind of sparsity I have, right? I only have the data of 100 records actually where the presence counts, presence of a disease count, because my objective could be to train a model to kind of predict whether a particular person has a disease. And for that, I have only 100 records, right? So there's a sparsity, yes, right? Resolution. Pattern depends on the scale. So let's say I have attributes like this. This x1 has values like this, and x2 has values like this. Right? Now, what should we do? When I have one set of attribute which can take a very small values in a range from, let's say, 1 to 50, while other is taking from, let's say, 1 lakh to 10 lakh and so on, what will happen to the model? What will happen is x2 will influence the model more because the values are large. So model will be biased towards x2, that x2's weight will come very high in comparison to x1. So what we want is, we would like to do a normalization where we will say, okay, that we'll do a feature scaling and bring the scale down of x2 to a certain range. Even I can do a feature scaling for x1. Let's say I want these values to be between 0 and 1 or 1 to 10. So that kind of feature scaling I will do for the values of x1, for the values of x2, and then give those values to train a model, so that model is not biased towards a particular attribute which has a higher range of values in comparison to the attribute which has a lower range of values. Then of course size, what kind of analysis I'm going to do, right, may depend on the size of the data. What kind of size do I have? I do have large or small, right? Then let's look at all these types of data sets. We have record, graph data, ordered data, right? So under record, we have a data matrix, which we have seen earlier. We have a document data, we have a transaction data, right? All these three we have seen earlier also. I can again show you a snapshot of these, but we'll quickly go through. We have a graph in the form of World Wide Web, the way the web pages are connected, the way the molecules can be modeled, right? It looks like a graph, the kind of bond that they share between them, right? Then, of course, the data in terms of spatial, temporal, sequential, and genetic sequence data, we have seen examples of each in our previous session. So I'll quickly go through to showcase these snapshots of these. Look at this. When you first look at record type data, right? This is one data set of records, right? Very similar to what we saw. Refund, yes, marital status, taxable income, and defaulted or not, right? So this is what, instead of cheat, we have defaulted borrower or not, right? So that's one thing. This is my transaction data. Here in one transaction, bread, soda, and milk are sold. In another transaction, beer and bread are sold. In third transaction, beer, soda, diaper, and milk are sold, and so on. This is my transaction data. And this, for this particular data, I can always do that market basket analysis, which two items are sold together, right? I can plan the layout of the store base by taking the, once I know that, okay, bread and jam are sold together, I can keep bread and jam together, right? Or I can run a promotional offer, right? So in such cases, this market basket analysis helps. Then you have a data metrics also, right? Then you have document term metric. This is important when you are actually doing comparison of documents, right? How comparison in a sense, which two documents are more similar, right? So I'm going to pick up the frequency of each word. Let's say this is one word, team. Team has appeared 3 times in document 1. 0 means document 2 does not contain teams. Document 3 does not contain teams, right? Secondly, the word coach. Word coach is 0 times in document 0, 7 times in document 2, 1 time in document 3, and so on. So later on, we will learn a technique known as cosine similarity, using which we can measure the similarity between the documents and come up with analysis where we say, okay, these two documents are more similar. Look at this kind of order data, which shows 4 different kinds of data. Like you have sequential transaction data, you have a spatial data as such, spatial temperature data, you have time series data as such, right? Genomic sequence data. So all these kinds of data do exist, and we can make use of all these kinds of data to do certain kind of analysis. How do we use it, and all that we are going to see later on when we start applying. Yes. This is another thing is graph data, as I told you earlier, right? So this can be used for various purposes, right? I can model certain real life situations. uh, I can see, okay, which web page is connected to the other web pages, using which I can create a link between them and model them as a graph. This is a benzene molecule, right? Where you see there are 6 carbon and 6 hydrogen atoms as such, right? And see how they are connected, and it looks like a graph as such. These are the hyperlinks you see here, right? Books. If you click on books, it will go to if you click on general data mining, it is coming to this particular page, right? So if you click here, it will go there. If you click on bibliography here, so this will go to this particular page. So all these are connected, right? See how the web pages are connected. So this is also forming a graph where the web page is acting as a node, and if there is a connection from one web page to other, that is represented by the edge as such. Look at the order data, the sequence of the transaction, the items and the events as such, an element of sequence. So A, B, B, D, C, D, this happens in a form of a sequence. Then there is some event D, then C, E in a sequence, right? So these are the sequence of transactions that might have happened, right? This is what you can see here also mentioned. So in transaction T1, person has bought this, transaction T2 this, transaction T5 this. So I want to learn the pattern. Maybe somebody has purchased a mobile, and later on he purchased a screen guard, and later on he purchased a mobile cover, and so on, right? So that kind of analysis I can do. What is being purchased in a sequence? How many sequential transaction does it exist? So customer 1 has made 3 transactions. These are the buying pattern. Customer 2 has done this. Customer 3 has done this. Now I want to figure it out. What is the sequence pattern buying of these customers, right? So genomic sequence data. I want to come up and learn certain patterns out of it. I can, and I do certain kind of analysis on the top of this, right? I want to find out two genes which are quite similar to each other, right? So I can pick up one genomic data, another genomic data, and do kind of cosine similarity or some other metric that I can use and find out which are the most similar. This is something the monthly temperature of land and ocean, right? So look at this for all the 12 months it is showing Jan, Feb, March, April, May, and so, and we can make use of this data and analyze the patterns. So kind of uh, spatial data, right? Changing over a period of time, right? Another thing that I said is that we will go ahead and do a data pre-processing because data suffers from a lot of quality issues. Now, what are the steps that we do in pre-processing? When I talk about quality, so these could be the issues related to quality, noise, outlier, missing attribute, duplicate record, right? Another thing is might need to do certain transformation sometimes uh, to my input data, right? Why those transformations are required, that we will learn. Some of these terms we have already covered. Dimensionality reduction, right? I just spoke about that. Feature creation, feature subset selection, we have spoken about that, but I'll just quickly iterate over each and every aspect, right? So far, if you have any doubts, please let me know. Any doubts? Are we good? May I have more responses, please? Okay. So let me move ahead with first thing is noise, right? Noise is what, when you look at set of data points, right? There are certain data points that behave significantly different as such, right? So it's an extraneous object that came in, right? And we want to identify this noise because noise actually modifies the original values. You must have seen, okay, if there is a cable, right, where the TV signals are coming, and if you switch on the mixer grinder near that cable, the signal will distort. You will see the distorted pictures. That's a kind of a noise that comes, right? We need to identify that and remove that noise. So this is what is being shown, that there are two sine waves of the same magnitude and different frequencies, and the waves are combined, and the two sine waves with a random noise. You can look at that. This is the observed signal. These are the two sine waves. This is the sum of two sine waves that have come in. And when you observe it, this is what the distortion that has come in, and that is actually a noise, right? So when you observe a data, you observe a noise in that, which is very different from uh, the original data. Next comes is the outliers. And it's very tough to distinguish between outliers and noise also, because uh, outliers are the objects that are very different from the normal objects, right? Let's say I am observing a set of 100 students and I see the height of the students fall between, let's say, 5'3" to 5'8" or 6, and suddenly I have a student with 7 feet. That's an outlier, right? it is behaving differently from the other normal objects. That is an outlier. Outliers may be because of noise, because of noise, the original signal gets modified. Now, whatever the data I am observing, the original data might have been modified because during the transmission or something, right? So outliers may be genuine outliers, that there exactly that person exists, or maybe it is because of noise, or normal value has been converted to an outlier value, right? Outliers are the goal of our analysis, right? We want to figure it out. Look at this plots as such, and whatever you can see in the red, right? These are very different, very far away from any of those dense points, right? This is one dense point, this is another point, set of points, this is another set of points. They do not belong to any of these group of points. They are far away from each and every group. So they are outliers, right? Very, very important in credit card fraud detection, intrusion detection. These are some of the examples of outliers. I've given you already the examples of these, right? Missing values. We have talked about it. There could be multiple reasons for missing values. People not share the information, right? Attributes may not be applicable to all the cases. So in that case, we'll end up in having missing values, right? So how to handle those missing values? Let's say I have a CSV file, right? When you have a CSV file, you have records like this. Right? So this is right. First record, second, this is first record, second record, third record, fourth record, and so on. You have records like that. Now, for this record, there is a missing value here. For this record, there is a missing value here. For this record, there is a missing value here. So what they say is you can delete all these, eliminate those records completely, which has one or the other missing values. Right, but I can do this when I have a lot of data with me. I have very limited data, then I cannot eliminate the records, because lesser the data, lesser the performance of the model also. But I have, let's say, some 20 lakh records, some 100 records have missing values, I can ignore them. I only have 1000 records, some 100 records have missing values, I cannot ignore them. Right? Then the other technique that I can use is I can use the estimate. How to estimate those missing values? Maybe I can take the mean, median, mode of those set of values and then replace it with mean, median, and mode, right? Anyone which fits more in line with them. Then I can come up with an imputation technique to handle those missing values, right? That's all. I can ignore the missing value. That's another way. Another thing is duplicate data. Data set may include duplicate objects also. The reason being that is sometimes you collect data from multiple places, right? Maybe you are collecting some customer data and the customer exists with the same email ID across multiple data. That's a duplicate data. So when you are aggregating the data coming from multiple sources, you need to find out duplicate records, right? So there are ways to clean the duplicate data, right? So we can find out which are the duplicate records and eliminate them. Then comes the aggregation. Aggregation is nothing but we are trying to reduce the data by combining two or more attributes, objects, into a single attribute, right? We want to reduce the data, we want to change the scale, we want more stable data, then we can do aggregation as such. So you look at the number of land locations and the standard deviation of average monthly precipitation, right? And now when you aggregate it, right, and you see that aggregation has kind of reduced those data points. So we are kind of changing the scale at one place and then coming up with these aggregations. More on this we will cover once we reach an actual data set source and show you how the aggregations can be performed, right? Sampling. I've given you enough examples on sampling today, right? Specifically on opinion polls and other aspects, that when you sample a data, you can randomly sample it, or you can sample it with some strategy, and that is known as stratified sampling, right? So typically what happens, I cannot train a model with infinite data as such, right? Typically we do sample and train a model, and that's what typically happens in opinion poll also. They are not going to each and every member, right, who has a right to vote and ask. They're just going to handful of people and they select their sample very carefully so that their opinion poll exit poll is exactly close to the results, right? So statisticians often do sampling because if you want to use the entire data set, it will be too expensive and time consuming. Imagine you want to come up with opinion poll by reaching to each and every person. That's not possible even, right? So sampling is typically used in a machine learning because processing the entire data set may be too expensive and time consuming, right? So if you look at these points here, you can sample them, the complete ones at 8,000 points you want to sample, and then the 2,000 points and the 500 points and all, right? So depending on what we are trying to do, right, we can do a sampling, but it should not be a very random sampling. Using a sample will work almost as well as using the entire data set if the sample is representative of the true data, right? Otherwise not. Otherwise that non-representative data problem will come. So use a sample that will work as well as using the entire data set. So the sample is actually the representative of the entire population, basically. That's what they're trying to say, right? So you can do simple random sampling with equal probability of selecting any particular attribute, right? Where you do sampling without replacement and sampling with replacement. The moment you select an object, right, you remove it from the population, that is without a replacement. With replacement, they are not removed from the population, and with replacement the object can be picked up more than once, right? That's what it is. When you do a stratified sampling, you simply do not do a random sampling, right? You actually, what you do is, let's take an example of those 1,000 patients, right, which we are examining. We have a data of 1,000 patients. I know 900 do not have disease while 100 have. Now if I do random sampling, any let's say 500-600 people can be chosen for training, right? And let's say all 600-700 people or instances which I have chosen for training are chosen from this bucket. So what will happen? Model will learn patterns, okay, for the people who do not have a disease, but model will not learn the pattern who have disease. Now if I create two partitions, partition 1 and partition 2, I'm sorry, I'm not sure why these lines are automatically getting drawn, which is not making much sense to me also. Okay, so basically I have a partition of 900, I have a partition of 100. So I'm going to take a sample from both so that model learns to find out, okay, who do not have a disease and who have a disease. Then only it will make sense, and that is a stratified sampling, right? Random sampling may pick up only the data from one class. Another thing that we do is discretization, where many times what we do is we convert a continuous attribute into a ordinal, or we do typically do an ordinal, right? So that is known as discretization. So let's say I have a height as, let's say, there are people with less than 5 feet, there are people in the range 5 to 6 feet, there are people in the range greater than 6 feet. So I have a height of different people. Some may have a height of, like, 4 feet 5 inches, 4 feet 7 inches, 4 feet 8 inches, 5 feet 2 inches. So lot of values can come in, and we call it as a continuous variable, right? The moment I convert this data into discrete values, what I'll say is, okay, less than 5 feet, 5 to 6 feet, greater than 6 feet. So I have three different values now, right? Maybe the people who are short of average height, and you can say third is good height, you can say greater than average height, something, right? So tall people basically, right? So then I can come up with these three values rather than those. So that is process is known as discretization. Binarization. The binarization is again those continuous variables are there, or even if categorical are there, I want to convert them into one or more binary variables. Now, what do we mean by binary? Binary has two, right? Now, if I have a continuous variable, I gave you an example of height, right? That was a kind of a categorical, we were converting it. Now, if let's say I came up with only one split, okay, people who have height greater than 5 feet 5 inches and less than 5 feet 5 inches. I can do both ways. So greater than 1, yes or no, right? So I'm able to convert a continuous into binary, which has two values, yes or no. Similarly, I can convert a categorical into two. Let's say there are a lot of categorical values. I can convert it into two, yes or no kind of a thing, right? So that is a binarization. Often convert a continuous or a categorical attribute, and then convert a categorical attribute to any set of binary attributes, right? Eye color, right? Height measured as low, medium, high. I can convert it into binary ones, right? Eye color, let's say brown or not brown. I'm interested in only this. So I will convert it into only two, brown or not brown. Then comes transformation. I gave you one example, right? Where one set of attributes was having the values in the range 1 to 10. Another set of attributes was having values 1 lakh, 2 lakh, 5 lakh, 10 lakh, and so on. So the scale on which they operate, that is quite different, and model will be more biased towards the attribute which has high range of values. So what we want is we want to transform them, right? So we can see, look at the simple functions that we can use to transform, right? We can do normalization. Either first thing is we can do this transform, apply these functions. The second is we can do normalization, which I was saying, refer to the various techniques to adjust the differences among the attributes, right? And take out unwanted common signal, example, seasonality, and so on, right? Any questions? I heard a voice. Okay. So the basic idea here is, right, when one set of attributes are very large while the others are small, let us do a normalization so that they are bring on to common scale. when you have a very large set of values, right, you can even apply functions to transform those values, right? Maybe those are not following a normal distribution and I cannot apply certain tests. If I apply certain function, the values may follow a normal distribution. They are compact and they are very in this particular range. So that is simple. Using simple functions, I can transform, right? So basically, I need to perform these steps so that my model which I'm training is not very much biased towards the values which are of higher range. Another point comes is the curse of dimensionality. Dimensionality means the number of attributes that I have. When you increase the dimensionality, meaning the number of attributes, the data becomes increasingly sparse, right? Increasingly sparse means there are some values that may be missing, right? So if you look at the number of dimensions, if you're increasing, this is something maximum distance minus min distance divided by min distance. Some metric that which we are trying to measure is coming down. And this is critical for clustering and outlier detection, right? And become less meaningful. Okay, these points will make more sense once if we are going to cover the clustering topic as such. But what I mean to say is, the more dimensions you have, the more challenges that you will have. We need to have appropriate number of features, and that's why the term uses curse of dimensionality. You see, the dimensionality is increasing while the performance metrics are decreasing, right? So in order to reduce that, we can avoid this curse of dimensionality by reducing certain techniques for dimensionality reduction, and one of them is PCA, right? Single value decomposition is also there, right? And in these techniques, what we are doing, we are trying to project the data, and we're trying to project in such a way that larger amount of variation is actually captured in the data, right? So you look at these points, right? I may represent these points with this particular line as such, right? And I may pick up one vector that will represent the principal components of this. That's all. How to do this in detail, we will look at it, right? Because a lot of mathematics will be there. My humble request is you revise your linear algebra and optimization part. Before I start these topics, you should revise that. Another way what we can do is we can limit the number of features that we want to select, right? I should not include each and every feature to my data set. I can remove certain redundant features. I can remove certain irrelevant features which are not required, and then of course reduce my data set and dimensions. I can come up with new features, create new features that are important and maybe much more efficient than the original attributes. These are the three things we have talked about: feature extraction, feature construction, and mapping data to a new space using some transformations like Fourier or wavelet analysis. Maybe the words are confusing and all, but just look at it what we are trying to understand as of now, right? Look at when I say moving the data to a new space. This was the sound wave that this was the sound wave that we are actually having, right? Sine waves. There is a noise also, right? And when we do the transformations and all, we get this sine waves with some noise separated out as such, right? So we are able to basically sort of map a data to a new space. You see the scalings are different. Here we have 15, 10, right? 5, 0, 5, 10, 15, and here we have 0, 50, 100, and so on, and then we have plotted against it. Next part is data analysis part, which is also very, very important, but I think it's simple also. We have almost all the things which I was talking about. Okay, maybe we'll spend 15-20 minutes and then we will cover it. So this is all some data set and all we should take and start exploring as well. Right. Okay, so I'll stop here at data analysis part, but my humble request is to all of you, keep taking notes as per your convenience, keep asking questions as much as you have in your mind about this. Maybe those may be silly questions that you feel that okay, I should not ask, but you please ask, right? Ask so that you set a solid foundation for this particular domain, and once you learn that, right, rest is all experimentation from which you are going to learn, right? Some basics are there which we should learn. Some of the things you will learn from experimentation, because we always say what data speaks will go by that. So you need to pick up a data set and do some analysis and then take a call, right? So I'm going to stop here. If there are any questions, I'm ready to take. There are no questions. We are good to wind up. Okay. Any questions? Shweta? Okay. Shreya Sarkar? No response. Naveen? Naveen? Divija Shekhari? Can somebody please respond? Yamuna Krishnan? I think, are you guys even in front of laptops? Asmi Chaudhary? Naman Nagpal? No response. See, this is very, very disappointing to see this.